不一样，它出来所以会不一样，所以你控制力变一样，让你改变是它的手法，不是只是这个声音而已。
好，开始。
还有其他的 rounder。
Challenge, please.
So we're going to challenge number 7. Challenge 7, please. 7. Accept.
像比如说一个是这样的质感，另外一个这样子的这样，所以也是 NS 这边是 S， 6个，它6个都是 N 头的，它如果一个是的话，一边就是完全 N， 另外一边完全是 S 头的。
它是有版的，还是 S， 那效果。
全部都是 N 的话，那它基本上是都是因为全是 S 的话，好像它也是 stable 的 stable 的，它也是会有。比如说你如果都是 S， 那这样当然是一定的。哦，可是如果是这样的时候，两边都是 N， 两边都是 S， 实际上是不一样的。然后如果都是 N 的话，我相信也都是不稳定的，只是说哪一个比较不稳定。所以我记得就是在讨论那个在市场里面，他们来定那个 user object 的时候，这个它就可以还有可以缺点的地方，是吧
？Sorry, Chairman。我刚才测试的时候，可以现在有没有显示？
啊，我怎么办？他说那个刚测试可以，现在又接不起来。
我电脑反应，它上面没有。
帮忙接一下。
XY configuration 的，只是得到它那个 rotation， 这个现在如果说完全放掉的话，还是会被吸在一起。
还有买过好的，
对，它在同一个电脑里面。
不理我。 控制一下那个我那个工程组的，是工程组的。那时间先暂停一下，
因为它整个大标也关不了。没跟他说。
对啊，因为好像说有的那个是不是有强讯号比较强的，因为接头都拔一拔，可能会有的讯号太弱就不行，就要拿比较强的来。
还是我们中间的来用，然后其实有电脑，
就换一个电脑在这边计时了，
就变成接中间的台。
我先稍微等一下，要不然接线就过来看看好了。
啊，但线要拉过来。
对，像这个线这样拉得过来吗？好像也不够长。对啊，可以试试看，那就是好。好。没有，直接换头，换头。可以吗？
应该会送一台过去，先用别的。
好，那我们这个那时间的这个话就是那个怎么办？你的那个
还是你
的那个电脑要不要拿过来这边给大家，就稍微还是可以看到。
哎，我切这个，你整台翻过去，你就电脑放那边对着他们。
线在这里哦。
不用，
你搬电脑，
因为这些没有了，对，你电脑给他们看一下。
对，电脑还是可以看一下时间，
至少看得到那个
看到那个球的那个形状的时间。
哦，那好。
所以你那边好了就开始了。好，都可以。
Honorable juries and fellow competitors, I'm a reporter from King Alpha Xinjiang High School, and today I'm going to report from number 7, giant selling plate. So for the problem statement, we can see when a large, thin, and flexible plate is bent. So it's bending, and it may produce a loud and unusual hawing sound. We need to investigate this phenomenon. So we'll be focusing on the bending and also the sound, which the main focus will be the different ways of bending to different results and different physical properties of the vibrations plates lead to different results. So here will be our content, and first we can see from a simple observation where we give a pressure from to the string of the plates, and it will have a acoustic sound is produced. And for the fast Fourier transform, we can observe the frequency that is produced by this vibration, and there will be a sound with a frequency, certain frequency with a biggest intensity, which for the problem statement, it requires us to investigate the loud and unusual howling sound, which we chosen to investigate the one with the biggest intensity under every experiment. And So he'll be our theoretical model. And first we introduce a classical plate theory from a thesis. And there we can get the differential equation of the motion. So we can, from the flexural rigidity derivation, we can later lead to the discussion about the boundary condition that we use for this experiment, which is the two sides is fixed and two sides is free to vibrate. And for this kind of boundary condition, there will be they use Rayleigh's method to determine the deflections function. And there are also different vibrational modes that we won't be discussing today because it's not a problem statement's requirement, but just showing that there are different vibration modes. And for the boundary conditions that we can get the deflection function derived from the thesis, and we can from this deflection function we can get our a simple model for the final frequencies formula that is derived on this formation for this certain boundary condition. And so from this part we can redefine our problem statement, and let's see it again. When a flexible plate is bent, so the sound is produced. So what does it mean? It means that we are going to investigate the bending and also the frequency produced as my interpretation. So in the bending, I'm going to investigate about the static part and also the dynamic part, which contains first the curvature and the geometry variations in the static investigation. And for the dynamic part, there will be the instantaneous force and also the material variations that are examined. And for the frequency that leads to the independent variables, that will be the fast Fourier transformation that we use to get the frequency. And for our experimentation, first is the static experiment, where we got our aluminum frame and the steel support to have the maximum fix that cause lower deviation of the plates. And we also have our violin bow to give it a force. And we use microphone to record the audio. And from a finite element method simulation, we can see that when we give the strain for the plates, that the deformation will be symmetric deformation. So our setup is usable. So for the procedures, we are going to first give the plates an initial curvature for investigation, and we use the violin bow to give the center of a plate a constant force. And we also record the sound via the microphone, and we can run the Audacity software and do the fast Fourier transformation for the frequency we need to investigate. So for the first experiment, we going to investigate the curvature of the plates that the dependent variables will be the frequency produced. And for our simple theoretical model, what we think is that when the curvature increases at one certain point, that the local density of that point will increase, which leads to the frequencies decrease. So from our experimental data, the curvature square value will have a negative relationship to frequency. And for the variables for the thickness of the plates, there we got also our simple model, and the thickness cube value will have a positive relationship with the frequency square as we showed. And we also do the filling line, and as the constants are shown on there, and it shows that it is truly a 3 times of relationship. And for the width of the place investigation, there will be the simple model shows that the width square will have a negative relationship to frequency, which we also use the power of 2 to do the fitting line, and it shows that yeah, it is. And for next part, we are going to invest this phenomenon dynamically. So we also got our aluminum frame and steel support, and we install our plate on it. So we also got our force gauge and a wood stick for the release method. And from the release, these plates will produce a sound, which we install microphone and in order to do the fast Fourier transformation for the frequency. So what our procedure is, we first set up the releasing device at a certain height, which from the Newton's third law of motion, it will give a constant force during every experiment. And so we release the device, and the device will come from the free flow, which we can record the audio produced by the plates, and we can do the frequency analysis. So for the variable, there will be the material of the plates, where in our theoretical model, they will be effective for two parameters, which is Poisson's ratio and also Young's modulus of elasticity. But the exact relationship is still unsure in our examination. But we can still see the relationship, like we do the steel's material, the nickel, aluminum, and plastic, and the frequencies are shown there. So, and there will be the thickness of the plates investigation, where there will be have a positive relationship with the frequency, and which can be shown here, and it will have a 3 times relationship with it. And for the conclusion part, first we're going to discuss there is some possible deviations, like if our frame and also our steel support is not fixed enough, or there will be little gaps that we cannot control, there might be vibrations inside of it, and so it might cause the deviation of our experimental data, and also the vibrate of this the aluminum frame or small acoustic sound may also cause a little deviation, that's the energy is transformed on it and due to the oscillation. So that is need to be considered. And for about the conclusion, let's look back to the promise statement again. So first, for the bending of the plates, which is the main factor that we are going to investigate in this investigation, that we investigate both statically and also dynamic condition. We'll discuss both of them, and we have different setup, and we do the different experimentations. And also the loud, for the definition of the loud and unusual howling sound, we define it as the frequency that can be acquired from the fast Fourier transformation and has the highest intensity for the loud and unusual howling sound. And for the explanation of the phenomenon, the beam theory, which is simplified to the plate theory and is applied in our equation, which we can get a simple model of the vibration of the plates. So for the final conclusion, that we can verify that the beam model theory can be applied, and also the fitting of different powers of frequency is matched to theory quantitatively. And also the static and dynamic setups are examined by like finite element simulations to examine the setup is producible, and also the deviation is discussed as previous. And for the conclusion that the curvature square value will have a negative relationship to frequency, and also the thickness Q values will have a positive relationship to the frequency, and which the width square will have a negative relationship to the frequency. And in the dynamic setup, we examine the material properties, and we will surely affect the frequency produced by the changing of Poisson's ratio and also Young's modulus of elasticity. And for the thickness Q value, will also have a positive relationship with the frequency. And I think that's all of our presentation. Thanks for your kind attention.
Question about voltage.
Okay. Can you tell me, do you do any experiments of bending a board by your hands or any machine?
Oh yeah, just like the observation video that we have already bent from our hands and shown it.
I mean, do you have the board, please? The board. Do you have to do any experiment like this?
Yeah, just like
Only one or any different materials?
No, we do it by the dynamic setup to examine it more accurately.
Can you show me your page 24, please?
Page 24, okay. So there will be page 24.
Can you play the video?
Sorry.
And what do you mean this machine can do? Okay,
This mechanism will apply a force on the plates, which by the Newton's third of motion, and I will give a force to the plates, and the plates will experience a acoustic phenomenon, which it will produce a sound that we can record and do the analysis.
Okay, can you show me your spectrum map?
Spectrum. Okay, first spectrum map in our observation is like this one.
And which is your fundamental tone and which is your harmonic number?
for fundamental tone, we think that under certain conditions, the one with the biggest intensity will represent the fundamental tone, and so the mode number should be 1.
And how about the harmonics number?
The harmonics number, yeah, there will be various harmonics happening, but we didn't consider it into consideration.
So you don't have a TRT number of it?
Yeah, we don't have.
Okay, that's all my questions. Thanks.
Thanks.
准备的时间。
不好意思，对，我没有。我们重算。
所以就是准备，现在准备。 Opponent, please.
Honorable judges and distinguished competitors. Hi, and I'm the opponent from Team PTP, and this is a problem statement, and we can see that the observation of their experiment is that the video showing the placement thing, and the theory is that they have a classical place theory, and data they have like the curvature of the place versus the frequency, the thickness versus the frequency, and the width versus the frequency. And the conclusion, you can see that they have a little gap to cause the deviation. So the pros of the reporter, we can hear that they have really nice reference, good observation, and also nice experiment set up clearly. But the cons, they are really lack of explanation of their theory, and also didn't tell us how do they do their data. Okay. So let's just come. Okay. So the first question, what is the size of the board or plates? The size.
Oh yeah, so it's like 1 centimeter width and also the like 13 centimeters length for the
How about
plates. The thickness we change it like mostly we use the 0.3 millimeters and in other like thickness part we use from 0.1 to 0.5 millimeters.
So do you show the different thickness experiments in your PowerPoint?
Oh yes, so in that's not this part. So it should be in this part. Oh yeah, this part. The different thickness that we have used in our examination.
Okay, page 19 please.
Page 19.
Can you show me what is this chart?
Oh yeah, so this chart represents the curvature square value to the frequencies value which to our experiments.
Okay, and let's go to your page that talking about the bending, the one that you have your hands on it.
Oh yeah, so here is our observation.
Okay, so have you tried to bend the both flat side at down and the stick side at down, or you only do this one? Like, I mean, do you want the bending like this, or you only have to do this one?
Yeah, we have.
Flat side at down. Do you do it?
This is just for observation, and yeah, for experimentation, we of course we put it vertically, just like this. So it's perpendicular to the y-axis or z-axis, putting forward.
So there's no any photo that you can show me you have used your board bending like this clearly.
Oh no, we didn't do that.
Okay, and next question. Have you done any different materials like wood, plastic, garlic?
Oh yes,
Of
we
course.
will.
And what is the difference?
Like the results we have shown that different results will lead to different frequencies produced as the fundamental frequency of each material. Yeah.
No more.
And yeah, I think that's what you want. Yeah.
Okay, thanks. And how do you see the air pressure in your measured parameters? Do you count the air pressure?
Sorry, I would like to ask the opinion to provide a view that why air pressure is significant to our phenomenon. Can you please tell me the relationship?
Okay, so so can you help me to turn the more brighter the machine? I can show the chart clearly.
It's okay, we can move on to the choose.
So like
Yes, please.
okay. Because like in our measurement we can see that air pressure during your experiments, if you have the flat side at top and the stick side at top, the air pressure will make the number become different.
Which number?
The number that you can measure in your
The frequency produced by, well, so horizontally and vertically it will make difference?
Yes, but that's why you can do from your future distance because we don't have enough, right?
No, can we just do a qualitative explanation that maybe we can use the backward to discuss your opinion?
So fine, we can go to the next one. And how many go to your page that have the microphone?
Okay, page that has the microphone. Here is the static
How do
sound.
you record sound, this one? Like, do you use dynamic or condenser?
We just record the sound and we do the analysis of it.
I mean the microphone. Is it dynamic or condenser? Is answer me dynamic or condenser microphone?
What do you mean by dynamic and condenser?
Okay, fine. Next. So, won't the microphone record the environmental noise? If you are not using a condenser microphone in a mute room, won't you record?
So your meaning is that the microphone is directionally to the sound, which means the one you were mentioning.
I mean there's different
So-
type of microphone.
Okay.
Like dynamics is for the microphone that you can record not all the sound. It's only record the most clearly sound in your what your board made. And the condenser microphone is the one that can record all the sound in the room, like according the
I
air
understand
conditioner. Yes.
that there is pre-filter of the one that you said. Yes. But in our experiments, this is pure audio, and we input it into the Audacity software to do a Fourier transformation for frequency. And I think and also from what we just mentioned, that we investigate for the highest intensity frequency, which if there is more noise, that the small noise intensity is not big enough, so that it won't be the main factor that will affect this phenomenon.
So you have used a density to avoid any environmental noise to make your record become fat, right?
Yes.
Okay, so next question. Do you change a new board every time you do a new record? Like, I believe you didn't do it only once, right?
Yes.
Do you change a new board every time?
Yeah, because of elastic fatigue, yeah, it's very important to do this, as you mentioned.
Yes. Okay. So, you don't have a paper. You don't have to use like a paper board, like a. Okay. And what kind of measure model do you use to measure your fundamental and harmonic spot number?
So just as we discussed before, we didn't do the harmonics part because it requires the loud and howling sound. So we count for the fundamental that's under every certain conditions that should be the fundamental frequency.
So okay, so you have used fast Fourier transform filter model, right?
Yes.
And do you use Fourier model?
What do you
Fourier transform.
Yes.
Have you used it in your charts?
Yes, so in order to get the spectrum like this, we need to use the fast Fourier transformation in order to get the hertz related to the intensity. So we can get the frequencies that are shown in our experimental data. Yes.
And one more question for material. Why don't you change different material during your experiments? Like you only have used one. You only have used is it Arlic or plastic?
Oh, this is Arlic.
This is Arlic. And the only material that you use is Arlic.
And that is for the observation of the phenomenon, which can provide us a good view of the phenomenon, which is demonstrated. And how about what's the opponent's view of changing different materials? Just, of course, we have done many like 4 material options. But what will be the view that we want to offer to the report?
Because like different board material can change a different elastic number, right?
Yeah, so just like our model shows, there is the Young's models of elasticity and also a portion ratio that represents the different place of squeeze deformation. And there will be 2 main factors that affects the frequency that is produced.
And can you help me to explain more about your theory quotation that you have mentioned? Not this one, the other theory.
Like which one? Part?
I'm going to change the pages. I'm not sure the pages. Like just.
Theoretical part?
Yeah, this one. Just help me to explain the theory quotient that you have mentioned.
So in detail, the plane theory is from the differential equation of motion that we can get the flexural rigidity will equals to the second derivative of the frequency and also density, which is the balance between the flexible rigidity, like just like some equations like the acceleration frequency, and we can use it to derive for our flexural rigidity. And for this model, we need to investigate in this kind of boundary condition. And in this kind of boundary condition, we didn't do the investigation about the deflection function, but this thesis offer us a clear view about how this deflection function is, and we can use it in order to calculate for the final frequencies formula, and we use it to do a qualitative experimental examination.
Okay, thanks. And how will you change to your spectral map? Can we use a blackboard, please?
Yeah.
Blackboard, okay. Just like for a sound wave, you can see a sound wave is like
Yes.
right. And for this map, do you choose only one wave or all the wave?
Of course, all the audio.
All the wave.
All wave, and that is able to do the frequency analysis.
But like during your record, you can see that the wave will be like this. Well, right.
Yes.
And so do you like you use this and this to transform into map in the same time, or you will do this in once and this is once, and then calculate it to find the number of the maximum?
Yes, just as the opponent showed us the view, that this is like one time of experiments, and this is the second time of the experiments. So during the two types of experiments, we can get the frequencies that is done in the various experiments, and we use it into our data that is presented in the experimental part.
Okay, thanks. And let's go back to the. And do you think it is important to analyze the wave of the plate?
Oh yeah, so, but as we have investigated that there will be various wave models there, and so it's quite complicated to do the analysis, but at this part, reporter doesn't think it will be the main part of the problem statement, but it still can be discussed. And the reporter had an opinion about we can use piezoelectric plates installed on the plates, and we can use it to record the voltage signal from the piezoelectric plates, and we can see how clearly the vibrational picture is. And what is your opinion? I would like to ask.
I would agree with you. Okay. And do you during your record, do you do like double open or triple open or only one open on your board, or you only do like, I mean, like you will make this place this side or not moving and do this then, or like both sides not moving and do this, or like you have to do it all open.
We just do the one that you've shown right now, but here the opponent offers us a good view about different boundary consideration, and maybe they will cause two different results as we only use this kind of boundary conditions, and which we can investigate in the future, and thanks to opponents of operating this view.
And that will be my point. Thanks.
Okay.
Summarize, please.
Okay, so for discussion, we can see that they only have do one kind of material and only the four side open measurement. But we can see they have really nice theory to show that they only have one type of material, but they can also find all these different experiments that we want to show, and we can only show in tons of different materials. And also in the spectrum map, we can see that the highest one is the number of this. It is clearly, that means that the record is very nice, that there is not a lot of environmental noise in it, and it will not disturb the Fourier transform during the audacity. Okay, thanks. That will be my discussion.
Question overview.
Okay, so for the first question, I want to ask both of you. So what is the main reason for us to hear the polling sound? So I want to go first.
I think it's the vibration of the plates.
Okay, and how about? Okay, and second is that what is the main factor to change the frequency?
Frequency, there are various frequencies. The various factors like the curvature and material thickness and the level.
Okay, so you think both of them will change it?
Will change under
And
the
how about
conditions.
the opponent?
I think that the frequency will change the pin that you can record of the boards I make. So the frequency will change if it's high or low. But it is fine. Okay, next.
Well, okay, and I want to ask the reporter, so do you think that the frequency here you got is equals to the natural frequency of the plate?
No, the natural frequency should be fine under resonance condition, and it's the fundamental frequency under certain conditions that we measure.
Okay, and next is that, do you think it will have the length limit of the plate that we can make the polling sound?
For my opinion, I think that the length should be boundary conditions if the force is big enough to make the plate this vibration.
So you think it'll have a limit?
We don't think so.
You don't think so? Okay, and how about the opponent?
Explain the question again.
Oh, okay. I mean that, do you think it will have a length limit of the plate that we can hear, oh no, that it will make a holding sound?
Yes, it will be the limit because if the number is over, the sound that is made will lower the pace that your ears can heard. So we think it will be a limit.
And how is the limit will be, or it is really small or really big?
And that will be our future discussion.
Well, okay. And next is that, do you think that the bending speed is the necessary factor that we can like hear the sound?
Pardon? The what factor?
The bending speed.
Bending speed. Yeah, it will be an interesting, important
No,
factor.
is that a necessary factor?
Yeah, if it's dynamically.
Okay, and how about the opponent?
Yes, it is.
Yes. And okay, so how about like if we bend the plate in really slow speed, will it also have the holding sound?
The holding sound depends. Well, our definition is loud, and which is the intensity.
And
So
please answer yes,
Yes.
or no. Yes, and
Yes.
how about
Because in our experience, different kind of material, the bending speed will be different. But like some of the material like garlic, will bend very slow, it will still be sound. But if you use a board, like a paper board, the bend very slow, the sound will not come out.
Thank you, time is up.
Okay, thanks.
You please.
Okay, so hello everyone, my name is Sharon from Team S601 and I'm the reviewer today and I'm going to review the problem number 7, giant sounding plate. And for the problem 7, I think we can skip it. And we mainly focus on the origin of the sound and how does the relevant parameter affect the result. Okay, so for the, sorry. Okay, so for the review of the report, their theory, and they talk about the classical plate and the deflection function and the Rayleigh method and Young's modulus. For their pros, I think they consider the Young's modulus, which is very important in this problem. But for their cons, they didn't consider the vibration in the gap of the device and the explanation of the theory. And for their experiment and setup, the they say about the curvature of the plate and the thickness of the plate and the material of the plate. And for their pros, they clearly explain of the phenomenon, and they nicely device to let the plate bending. But for their cons, they didn't have a different bending method and bending frequency. And next is about the data analysis. They have the compare between the frequency and with their parameter. So for their pros, I think they nice define the holding sound, and they have good way to get the frequency data. But for their cons, I think that length of the theoretical line and some parameter didn't have enough data. Okay, and next is the review of the uphold. So for the short question part, they talk about the bending method, and for the pros, I think he points out the reporter didn't consider the harmonic number. And for his cons, I think he used too much time to asking the question which the reporter didn't do. And for the discussion, they talk about the bending method, the material of the plate, the air pressure, and the accuracy of the experimental method. And for his pros, he pointed out the air pressure will be different when bending, and he considered the collect sound will be not accuracy because of the microphone. And for his cons, he used too much time on the experimental accuracy and to focus on the bending method, which the reporter didn't mention in his presentation, and didn't discuss the comparison between the theory and the data. And next is the discussion time which the opponent asks to the reporter. So the opponent asks that the bending method is just using hand or have a device to control. And the reporter say that the observation video just use hand to bend the plate, but they have a device to control the bending amount in the experiment. And for our opinion, we think that the reporter's device is like to control the amount of bending, but that device cannot change the vibration, frequency, or the bending methods. And next, for our question is that we asked that what the main factor to change the frequency. And in our opinion, is that the material of the plate. And the reporter said that it's the curvature and other parameters, and the opponent didn't answer this question. And for this question, I asked about what is the main reason to hear the sound. And we think that it's the deformation of the metal plate, and both the reporter and the opponent say the vibration. And next I asked, do you think there is a length limit to make the holding sound? And I think yes, and if it is too small, we can't hear the sound. And the reporter said no, and the opponent said yes, and he thinks it should be a visual word. And that's all for my review. Thank you.
Conclusion, please.
Okay, so in the part of our presentation, we present some boundary conditions theoretical model, and we also examine our experiments in dynamically and also statically. And opponents offer us some view about our future works, which is different boundary conditions consideration, which we didn't do in our investigation, and that is very interesting that we can do for like different bending methods and different materials, just like the opponent once want to say about the paper or some other elastic materials, and that is interesting facts that the opponent offers for the reporter. And for the reviews parts, that reviewers offer us a more view about how the phenomenon should be considered, and I think that's I'm going to thank both of the opponents and the reviewer for the improvements for my investigation, and that's all of my concluding remarks. Thanks.
I actually don't know what the holding sound sounds like. So if you cannot play a video, an audio, you can sing for me. Sure.
I think this is a sound that demonstrates the holding sound of the Trump statement.
Yes, we are going with him. Something like this is right.
No, we also do that, and it sounds like that. But the material we use is the metal, and it'll be like some difference, but well, it's like a normal shows.
So I think the definition of this using a free transform spectrum to define a Howing sound is just doesn't make any sense. The other thing is about this vibrational normal mode. It can be just very small vibration. You can define those modes. So what has that to do with this Howing sound? I don't feel there's any clear relation to it.
Yeah, sorry for this point that we didn't do, but our point is on the loud sound, so which means the intensity, and that is what our problem do, and that is our miss point. And thank you.
Pardon the question. Would you mind to describe how unusual the Howing sound is?
For the unusual Howing sound, I think for Howing this word, it must be mixed by different frequencies, because such as this sound, it won't be just placed by one certain very high frequencies. So if we are going to consider Howing sound, it should be consider the different modes, that how many modes are there for just like the standing waves equation, that there are various modes compose a sound that is produced, and it will be relevant to many parameters, yeah, just as shown.
This sound is just one frequency or composed
It's composed by mode.
I think it will define by the wave we can see that we record. Because different material, we can see different wave, and so it means we can define a different sound of it.
I think for the question, I think it'll have many like frequency for the whole sound, and for the comparison, they need to compare it for both of those frequencies.
Okay, so for the questions Julie just asked about the investigation of Howing sound, that the report reason is not going to investigate it is because we cannot be sure that which frequency that has intensity is not caused by the vibration of a plate. So it's hard to do the measurements of what mode is actually composed in the sound audio, and that's our reason.
Okay, my question is, the filter experiment for the plastic and the aluminum, so which one get a higher frequency and which one has larger amplitude?
For the amplitude, it should be the aluminum, and because like the Young, I think it's about the Young's modules, and for the plastic, it will have lower frequencies and also lower amplitude, just like we have shown in our slide. And yeah, I think the main factor about it is the Young's modules, which affects the vibration of it.
You agree?
I will agree with the reporter's answer.
I think it's metal.
You agree the reason for the same. Okay, thank you.
Nuclear marking time. For reporter, 7, 6, 7, 6, 7. For opponent, 6, 6, 7, 5, 6. Go review. 7, 6, 8, 7, 7. The end. Thanks all. Have a nice